Alright, welcome one and all to another quantum adventure with Jeremy, yours truly. So today I'm gonna be covering some, excuse me. So quantum neural networks, of course. That's what I'm gonna be covering today. I'm gonna try and edit the video while live, so I apologize if I'm a little slow at this. Okay, so let's see. Quantum neural network. Yes, that's good. So mostly, I guess I'll cover what like IBM has to say about it. I'll try and find out if any other companies or any other major researchers have anything. There's plenty of papers out on this subject, so I definitely recommend reading some papers. I'll try and share some in the description. But yeah, that's good enough description for now. I'll edit it later. So, um, let's get into this with PennyLane. So, quantum machine learning so far. Um, let's see. So these guys use PennyLane and TensorFlow. And then optimization of variational quantum algorithms. Recently, a big effort by the quantum computing community has been devoted to the study of variational quantum algorithms, VQAs, which is different from my last video, VQEs, variational quantum eigensolvers. Those were used to solve like state problems, and you could represent different problems as state problems. So a lot of this, there's so many different uses for quantum computers, and most of them are going to be in like finance or simulations, just because they simulate things better than classical computers do, because we live in a quantum system, not a system made of ones and zeros. At least I hope it's a quantum system, because anyway. So these leverage quantum circuits, right, and shaped and tunable parameters. The idea is similar to classical neural networks where the weights of the network are optimized during training. Similarly, once the shape of the variational quantum circuit is chosen, something that is very different and sensitive to the particular task at hand, its tunable parameters are optimized iteratively by minimizing a cost or loss function, which measures how good the quantum algorithm is performing. So, okay. A bunch of parts in creating a quantum machine learning algorithm. A major challenge for VQAs relates to the optimization of tunable parameters. So this is like, what can I put into the problem, or what can I feed this algorithm to, and which was shown to be a very hard task. Parameter initialization plays a key role in this scenario, since initializing parameters in the proximity of an optimal solution leads to faster conversions and better results. Thus, a good initialization strategy is crucial to promote the convergence of local optimizers to local extrema, and to select reasonable good local minima. Okay, by the local optimizer, we mean a procedure that moves from one solution to another by local changes in parameter space. These are opposed to global search methods, which take into account large sections of parameter space to propose new solution. One such strategy could come from the classical machine learning literature. So this is a classical machine learning algorithm, right? And so I believe what they're saying is mixing the two So let's say we have a quantum machine learning algorithm and we have a classical machine learning algorithm. So they're going to be using both of the best of both worlds, just because right now quantum computers are not, uh, they're not, they're really error prone. They have a lot, this thing called noise, and qubits have issues with noise, like they basically lose all the information, or it returns different information because of noise. So by mixing the best of both worlds, the classical computing side and the quantum computing side, you can get way better optimization. So let's see what they cover in their solution. By building on results from meta-learning literature and machine learning, authors propose to use recurrent neural network (RNN) as a black box controller to optimize the parameters of variational quantum algorithms. So they're using a classical machine learning RNN to optimize the parameters of the VQAs. As shown in the figure below, the cost function used is the expectation value, and then they have brackets h theta equals wave function theta h wave function theta of a Hamiltonian h with respect to the parameterized state bracket. So that's a bracket notation with the wave function and theta, evolved by applying the variational quantum circuit to a zero state. And then they have, so this represents a bunch of qubits, whatever you have filling in that qubit space. That's what that means. It's just like it's in bracket notation. And I should probably make a video of bracket notation, just because that would be helpful as well. And I'll even make a video of like learning math with y'all, just because I need to learn math better. And I'm not really good at calculus, but I've been learning steadily, and I'm pretty hard-headed and stubborn, so I'll definitely learn it anyway. It's just the amount of time that it'll take to learn it. So given the parameters theta t minus 1 of variational quantum circuit, the cost function y t minus 1, and the hidden state of the classical network ht minus 1, I wonder if that's like kind of like acting as an oracle. Sorry, I just learned about oracles like a week ago or two. So at the previous time step, the recurrent neural network proposes a new guess for the parameters theta t, which are then fed into quantum computer to evaluate the cost function yt. By repeating this cycle a few times, by training the weights of the recurrent neural network to minimize the loss function, excuse me, a good initialization heuristic is found for the parameters theta of the variational quantum circuit. Yes. Well, I'm just going to look something up real quick, make sure I'm saying that right. Yep, it is theta. Sweet. It's like I'm learning with y'all. Anyway, at a given iteration, the RNN receives as an input the previous cost function yt evaluated on the quantum computer, where yt, oh, I think okay, where's the estimate of h Hamiltonian within bracket t, as well as the parameters theta t for the variational circuit was evaluated. The RNN at this time step also receives information stored in its internal hidden state from the previous time step ht. The RNN itself has trainable parameters. What is that? Is that phi or psi? I know, I'm still learning all these math Greek symbols, phi, and trying to remember what they stand for. And hence it applies to the parameterized mapping ht plus 1 theta t plus 1 equals RNN phi, uh, and then parentheses ht, comma theta t, y t, comma, which generates a new suggestion for the variational parameters, as well as a new internal state. Upon training the weights phi, the RNN eventually learns a good heuristic to suggest optimal parameters for the quantum circuit. Thus, by training on data set of graphs, the RNN can subsequently be used to provide suggestions for points on new graphs. We are not directly optimizing the variational parameters of a quantum circuit, but instead we let RNN figure out how to do that. In this sense, we are training the RNN how to learn how to optimize a variational quantum circuit. See, it's genius. Have the computer learn. So it's like it's telling, okay, so classical machine learning computer, you're going to learn how to optimize the quantum machine learning computer for me. Which I think is kind of genius. But nerd talk, you know. So VQAs in focus. QAOQ for max cut. There are multiple VQAs for this hybrid training routine. So this is also called as a near-term algorithm. If you haven't heard of that, just because there's a lot of buzzwords in this type of space, and I'll try and explain them as much as I remember to. You can also leave it down in the comments, you know, like if you have questions or something like that you want answered, definitely let me know. Right, where were we? So some of them I directly analyzed in figure 1. Right? Cool. Let's go back up to what we're reading, which is nice to give you a bunch of code so that you can try it out yourself. In the following, we focus one such example, the quantum approximation optimization algorithm for solving the max cut problem. Thus, referring to the picture below in the shape of variational circuit is one dictated by the QAOA and such a quantum circuit is used to evaluate the cost Hamiltonian H of the max cut problem. Check out this great tutorial. PennyLane demos. Let's check out their demos and see what we can do here. Okay. Bunch more math. Got it. Okay, so the import PennyLane is QML, quantum machine learning, I guess. Add it to the Hamiltonian H gate. I wonder if I could like represent this. I probably could. I could convert this to Qiskit and try it out in Qiskit, but it's kind of cool to see how different libraries hold up against Qiskit. Just because I learned Qiskit through this qubit by qubit summer program, which was pretty cool. It's mostly supposed to be meant for high school students, but honestly, I will do anything I can to learn about quantum computers because they are seriously going to change the world. Like, as soon as we have a quantum computer that can hold at least like 500 qubits, like that's a pretty huge milestone. And then 5,000 qubits is even bigger milestone. And 5,000 qubits, we could pretty much outperform the universe, which would be pretty cool to do, because then, yeah. But honestly, I think you can do that in your brain too. Like, if you learn, you know, what quantum computers do, and you can simulate that in your own brain, Sorry, I'm getting ahead of myself. Good stuff. I just like learning. So, I'm just reading over this article a little more. So they cover a bunch of stuff. I'm gonna let you all learn more about this one. It's pretty cool. Oh look, they let you download the notebook. What perfect simplicity right there. That saves so much time. So yeah, if you haven't already, definitely download the notebook so you can play around with it. So I'm going to be playing around with it with Qiskits, and I'll also cover Qiskits, like what they say about quantum neural networks. But it's nice that they let us download the notebook, because the best way to learn for me is to actually do stuff with it, you know. Not just see it, but you know, actually perform. Because for the longest time, I had been just reading about stuff and reading about programming, and like, you know, I wasn't really getting into actual programming for myself and things like that. Now I'm doing it daily, which is, I think, a lot better way to learn, and it'll give you real world experience a lot quicker. So definitely try out some of these. Once you create a login with IBM Quantum Lab, sign in, and then download the Qiskit textbook if you haven't already. It should be there for you. I think it was there the first time I logged in. These are a bunch of like qubit by qubit tutorials that we did during summer school. So it's pretty cool stuff. I'm enjoying it so far. And let's get back to this. So now we're going to be talking about what IBM is using for QNNs. Let's see. This demonstrates a generic quantum neural network provided in Qiskit machine learning. The networks are meant as a application agnostic computational units that can be used for many different use cases. So that's the key word right there. It can be used for many different problems. Depending on the application, a particular type of network might be more or less suitable and might require to be set up in a particular way. The following different available neural networks will now be discussed in more detail. So they're going to cover 4 different. I think I'm going to cover just the neural network, maybe just this first one, just because I'm kind of pressed for time. Let's see how long I'm streaming for. Okay, yeah. So I'm trying to keep all my videos under 30 minutes, but we'll see where this goes. If I get into a groove, I'll get into a groove and keep going. You know, it is what it is. Oh, let's run this. To run this is just Shift Enter. If you haven't run a Jupyter Notebook before, Jupyter Notebooks are pretty cool. They let you put, you know, documentation alongside with code, and so it makes it a lot easier to explain things. This is a comment right here, Python comment. This is all written in Python. Qiskit is a Python library. And let's see, so setting up some variables, setting up the gradient. Okay, then they're going to select a backend. So this is the simulator. It's a quantum simulator. So they're setting up a quantum simulator with 10 shots. That's what that is. And let's run that. Okay. Now, for problem 1, the neural network represents the interface for all neural networks available in Qiskit machine learning. It exposes a forward and backward path taking the data samples and training weights as inputs. A neural network does not contain any training capabilities. These are pushed to the actual algorithms/applications. Thus, a neural network also does not store values for trainable weights in the following. Different implementations of this interfaces are introduced. Suppose a neural network called NN, then the NN dot forward inputs and weights pass takes either flat inputs or the data and weights of the size NN dot num inputs and NM dot num weights respectively. Neural network supports batching of inputs and return batches of outputs of the corresponding shape. So opflow QNN, let's see, takes a parameterized operator from Qiskit and leverages Qiskit's gradient framework to provide the backward pass. Such an operator can, for an instance, be expected value of a quantum mechanical observable with respect to parameterized quantum state. The parameters can be used to load classical data as well as represent trainable weights. The opflow QNN also allows lists of operators and much more complex structures to construct more complex QNNs. Fancy. Okay, always start with your imports, and let's see if I can explain kind of what's going on here. So we're setting up some parameters, right? Input 1 and the weight, and we're assigning a quantum circuit to QC1, and then we're adding an H gate to that quantum circuit. Then we're adding a RY gate to that quantum circuit with the parameters 0. Okay, and then an RX with the parameter. And this, I'm not too sure. QCSN state FN. I think that's probably going to try and store the state of QC1 after we've applied all those operators. Ouch, my brain is exploding and imploding, and it's all doing all sorts of leaps and bounds right now. H1 equals state, poly sum op from the list. Okay, and then it gives it a bunch of operators and math. Okay, combine operator and circuit to objective function. So let's run this. And so we get this output composed. Oh, because it prints it here. That makes sense. So this is the type of circuit it would create. So an H gate, RY, RX. So input 1, weight 1. That's kind of cool. Now we're going to construct opflow QNN with the operator and the input parameters, the weight parameters, the expected value gradient and quantum instance. Okay. Here, let's play some of this YouTube Google music. This one's called Back to the Future. Cause my brain hurt, and I need something to distract me just a little bit while I'm learning this. I'm learning this with you, so be nice to me in the comments. I'm just kidding. You can be rude or savvy, spicy if you want. As long as it's good criticism, I'll take whatever good criticism I can. Even if it's just 5% good. And then I'll drop whatever is not good. Okay, so did that. Run that. Let's just keep running all this actually and see what we get. Okay, so we ran all these, started here, expected value, gradient, quantum instance, okay. Input random values and weights, QNN pass forward to an array, gives back another array. Okay, contain multiple observables and list up. So create more complex QNNs. List up. That's cool. So these are just generic machine learning algorithms that they allow. They're teaching us. IBM, I guess. And then they have like the IBM thing license. So this is all IBM's code. I haven't changed it or anything. I'm just reading over it and learning. And that's the whole point of this video. Okay, 2-layer QNN. Oof. Wow. That stuff's heavy. Alright. 2-layer QNN is special upflow QNN on n qubits. That consists of first a feature map to insert data, and second to enhanced. I can't say that. That is trained. The default observation is z to the power. I've never seen that symbol before in my life. What is that? Let's check it out. Mathematics symbols for a tensor product. Okay, so at least I know what a tensor is. So z tensor n. Huh. Cool. I'm also going to try and make a video about matrix multiplication just because I need to review that too for myself. Feature map. I'm just running all these and checking out what it gives me. But definitely, while you're in here, you know, check stuff out. Play around with some of the values, see if you can if you can apply this algorithm to an actual real world problem, just because that's like the best way to get learning and also to actually help the world, because you know, learning knowledge is cool, but if it's never used, you know, it's kind of a downer. I'll cover this last one just because I mean it helps me learn too. So last machine learning algorithm they have is called a circuit QNN. The circuit QNN is based on a parameterized quantum circuit. This can take input as well as weight parameters and produce samples from the measurement. The samples can either be interpreted as possibilities of measuring the integer index corresponding to a bit string or directly as a batch of binary output. In the case of probabilities, gradients can be estimated efficiently, and circuit QNN provides a backward pass as well. In the case of samples, differentiation excuse me, is not possible, and backward pass returns none. Further, thus, circuit QNN allows to specify an interpret function to post-process the samples. This is expected to take a measured integer from a bit string and map it to a new index. A non-negative integer, in this case the output shape, needs to be provided, and the probabilities are aggregated accordingly. A circuit QNN can be configured to return sparse as well as dense probability vectors. If no interpret function is used, the dimension of the probability vector scales exponentially with the number of qubits, and sparse recommendation is usually recommended in case of an interpret function. It depends on the expected outcome. If, for instance, an index is mapped to the parity of corresponding bit string, i.e. to 0 or 1, a dense output makes sense, and the results will be a probability vector length 2. Oof. Alright, let's run some of this and see what we get, huh? I think it's actually looking different than what they had previously, just because Qiskit's also changed. See that? Qiskit's also changed from the last time this was probably made. So, alright, let's see if we can fix any of it. While we're here, trace back, module line 2. A sparse library is required to use the OK. You can install it with pip. Oh. How did we not get this? Maybe we need, I guess it's saying that we might need some more dependencies. Let's find info. DOK. Okay. Matrix. Leave it. Probability gradients. Here, let's just research the exact Notice I don't use Google just because, wow, they have too much of the world's data anyway. Sparse library, really? You can't find anything. Wow. Well, let's try Google. So rude. Let's see what you got. So it says that we have a missing library. I don't know. That doesn't make sense. But let's see if we run it here, it'll actually go through it, cause yeah, I didn't think so. This is like one thing. I apologize. I don't want to spend too much time on trying to solve this problem just because it's like it's a problem with Qiskit's environment, not like, and I don't have an environment set up quite yet just because I learned programming on a Mac computer, and Yeah, this would be like if you wanted to add it to your local environment, not to like IBM's environment, which is an instance. Anyway, we covered 3 of the 4. The 4th looks like some of the libraries are, because Qiskit is pretty new, looks like some of the libraries just aren't, they changed or aren't working in the code anymore. So that's definitely something to look out for when you are using some of these, is that Qiskit is still in development, so is Circ, and I think Circ is Google's quantum solution. I guess aside from that, we can look at others, what they have to say about quantum neural networks. FinTech, time series functioning. Yeah, so this is also, I think they're going to be using it for finance. That's probably what they're going to try and use it for. A lot of this is high level stuff, so I definitely commend you for trying to understand it with me. Thank you so much for being here. Thank you, and I will see you in a week or so. I'll try and post these weekly. I'm just not too sure, just because I don't have a set time yet, but yeah, I hope you enjoyed it. Like and subscribe for more quantum videos and quantum adventures with me. See y'all.